So in this question, we're given some data, and the table shows the number of maths teachers working in 8 different towns. That's going to be the X variable, and the number of burglaries committed in a given month in the same 8 towns, and that's going to be the Y variable. The very first thing we've been asked to do is to calculate on our calculator, it's a statistical calculator, the PMCC, the product moment correlation coefficient, between the number of maths teachers and the number of burglaries for towns A to G. Although we've been given data for A to H, we're only asked for A to G. And I think you can see in H the data's incomplete, and that's why we've not been asked to calculate it. Okay, just using A to G, these values are going to go into our statistics table, list 1 for the maths teachers, list 2 for the burglaries, and we get a correlation coefficient, an R value of 0.79. Okay, so in part B, we're actually asked to interpret the value of the product moment correlation coefficient in the context of the question. So we have strong correlation. In the context of the question, we can say there is strong positive correlation between the number of maths teachers and the number of burglaries. In part C of the question, we're asked to test at the 5% level of significance whether there's evidence of positive correlation between the number of maths teachers and the number of burglaries for towns A to G. So this is going to be a hypothesis test as usual. First thing to do is we need to set up our hypotheses. H0 will be that rho equals 0. There is no correlation in the town between the number of maths teachers and the number of burglaries. And the alternate hypothesis H1, that actually there is positive correlation between the number of maths teachers and the number of burglaries. Let's be careful here. We have already calculated R, but R is only about our sample. We're trying to see whether or not this evidence from our sample is strong enough, convincing enough for us to make inference about the whole population. So here we're talking about rho, the whole population. There is no correlation, or in the whole population, there is some positive correlation. Okay, so as usual, after these, we're going to go ahead and write down our n value and our significance level. So n equals 8, significance level of 5%. That's enough for us to calculate our critical value. We're going to the tables. So reading across for 5% and down to n equals 8, we get a critical value of 0.6694. If our calculated correlation coefficient is stronger than this. So let's just see it on the diagram. So we have our boundary here at 0.6694. Any correlation coefficient we calculate in this shaded region would suggest that there is evidence of positive correlation, would suggest that we can reject H0. We've already calculated our correlation coefficient. 0.7922 is stronger than our boundary value, stronger correlation than our critical value. From here, we can draw our conclusions. Firstly, we'll just make a comparison of the two values. So our calculated value, 0.7922, is stronger than the critical value, 0.6694. We have a significant result. From here, we're going to need two conclusions, one mathematical and one contextual. And we can say that we have enough evidence to reject H0, that's our mathematical conclusion, and we have enough evidence of positive correlation between the number of maths teachers and the number of burglaries. Okay, so that'll be 4 marks for the hypothesis test, the actual conducting the hypothesis test. We're then asked in part D to comment on the statement, the maths teachers are likely to be responsible for the burglaries. Some people may come to that conclusion, but actually we don't have evidence of that. All we know is that where there are more maths teachers, there are more burglaries. It doesn't mean that the maths teachers are causing or committing those burglaries. There may well be a different factor that is connecting them. So for instance, the first thing that comes to mind for me is actually, if the town has a larger population, we would expect there to be more maths teachers. We would also expect there to be more burglaries. There's more residents, there's more houses to be broken into, there's more criminals. So, yes, a larger population is going to have more maths teachers and more burglaries. It does not mean the maths teachers are committing the burglaries. There will also be more branches of Starbucks. It doesn't mean that Starbucks is causing the burglaries or that maths teachers are attracted to the town because of the Starbucks. There will also be more gyms in this town. It doesn't mean that gyms are built because there's more maths teachers. It doesn't mean that people who go to the gym are committing these burglaries. It doesn't mean that these burglaries are funding the building of gyms. These things are not connected directly. There's a third variable that is causing these independent variables. Okay, so just look out for that. Even though we've tested and we've demonstrated that there is correlation between them, correlation is not causation. There is usually and likely to be a third variable involved. Okay, so in part E of this question, we're asked to use linear regression to estimate the value of K. There was an unknown value for the number of burglaries in town H. In the table, it was just shown as K. We have enough information to put together a regression equation for a potential line of best fit. Now, all of this was on the same screen that we calculated R from. We have a value for A and we have a value for B. We always choose the form A plus bx, which makes A the y-intercept and B the gradient. So we'll just substitute those values here. So gradient of 0.408, intercept of 15.0526, and we'll just substitute x equals 40. When x equals 40, we get y equals 31.3726. So, using our regression line, that is our estimate of the number of burglaries that will be occurring in town H.